Okay. And so we distinguish between two orbits of comets. So one is like this short period comets, also periodic comets. They're coming from this Kuiper belt, so near the solar system. And then you have this long period comets. So they're coming, so emerging for this Oort cloud. And so this, let me say, this fact of Bernoulli, we can formulate it statistically in hypothesis testing. So it is like a question, yes or no, is there an almost coincidence? And more precisely, is there, for example, an uniformity, are they, so orbits of comets, are they uniformly distributed? And why directional statistic? So I hope that the online guests can also see what I wrote on the blackboard. So imagine here you have then the spheres. So this is our Oort cloud. And you have then, let me see, for example, here, a long period orbits of the comets. And this one you can visualize it. So you have here a lot of one. And this one you can, for example, visualize all the unit factors. So here's length is not important. And this can represent it then on the spheres like as a point. So this is the data here that you have. You call it spherical data. For example, Shogo, he explained circular data on the circle. And then you have a lot of varieties. Like for example, on the torus, you can do, if you have the data on the torus, you call this toroidal data. You can also have on the cylinder. Driving is not good, so on the cylinder. So directional statistic, in other words, is statistics supported on a Riemannian manifold, like the spheres, the torus, cylinder, etc. So let us be more precise. So given an ID is simple of points on the hyperspheres, so this is our SD, of our unit random factor X, and P is then the probability distribution, and unif SD is then our uniform measure on these hyperspheres. So I think this is no surprise. So testing uniformity on the hyperspheres, you can formalize in a null hypothesis testing. You have then the null hypothesis, it is uniformly distributed, against it is not. And here I listed some well-known uniformity tests. So you have here the classical one, with Rayleigh test, Cooper test, Fastenstat, etc. And these are more recent tests. So you can have a test based on random projection that was proposed by Costa and Albertus and all. Corridor distance, that was during the Adista conference proposed by Garcias and Portuguese. Then one also from Halland and all, based on measure transportation, and one really recently, it's more a particular one, and data-driven stabilization of goodness of fitness test. So there are a lot of other tests. I only listed the uniformity tests that are used to space science application. So let us come back to the problem. Is it working? Yeah. Problem of orbits of comets. So we can, the question is, okay, are the comet orbits uniformly distributed? So here, as I explained before, So we use then a test of uniformity of the normal factors, in this case of long period comets. So here you have then a picture what I tried to draw here in the blackboard. So Graz in Portuguese did it a little bit better than me. So you can really see here the orbits of long periods comets. So it is observed from 2007 to 2002. And then here on the picture on your right, the normal factors. And using one uniformity test or various tests that I've shown before, the outcomes is that there's no statistical evidence against uniform distribution. So here I listed the paper that use uniformity test for this kind of application. And the question that one can ask, is there an observational bias or evidence against non-uniform in this Oort cloud? So this is an example how to use, for example, uniformity test, this case for the orbits of comets. Another interesting example is, so next slide, please. Okay. Is the craters, for example, on planets and moons. And this is very important because it helps us to understand how old the planet on the moon is. It is by counting the craters that we can understand, okay, not understand, but get more information about the surface of a planet, respectively of moons. And here's the same. So we can reformulate it in a statistical word. Okay, are they uniformly distributed? So the analysis was done for Venus, for Mars, and Rhea. Rhea is a moon of Saturn. And it distinguished between two craters, so the small craters and the big craters. And here you can also use again an uniformity test. And here again, it's also no statistical evidence to reject the null hypothesis test. And here you can see, so on your left, you have the Venus surface. So the black points are the craters detected. The same is for the moon of Saturn, Rhea. So here it is like the green dots. And on the middle, you can really see the p-value for the different planets and also the moons. And the most widest three examples, Venus, Mars, and Rhea, because you can see maybe this is too small, but if you check the p-value, so CVM, AD, and RT, so these are the different tests used to compare. So it is the Kramer, von Mies, Anderson, Darling, and Rotterdam test. And the most interesting case is really Venus, Mars, and Rhea. And the explication of this, let me say, rejection, it could be explained that the Venus has really a dense atmosphere. So it filters, let me say, small meteorites that impact on the Venus and create these craters. And for Rhea, it's maybe a crater saturation or a diminutor of these planocentric impactors. And here again, you can see those papers that use then a uniformity test, except this one. So for this one is an asterisk. Here's another method applied to test if there's an uniform distribution for the craters. Another example, which is very important, we're at ESA. I'm working on this study because I am in the Space Weather Office. So we're analyzing our sun. And our sun has like sunspots that are appearing on the sun surface. And here we can ask the same thing. Are they uniformly distributed? Here we need to take a little bit care, because the sun is like, we call it a cycle, so it is 11 years. And so there's a peak. So here you have less sunspots, and then where there's like the peak, you have a lot of sunspots. So where the sun is really powerful, and then less. And here there's like the critical, where it has a lot of sunspots and could be also dangerous for us, Earth. We are protected from the Earth magnetospheres, but for example, our satellites are not. Okay, and it's very important to study the sunspots, the evolution, and to track them. We can use direction statistic. So one way to do it is to test if they're uniformly. For example, here in this case, it's not really like no rejection of this uniformity. Here it was for the cycle 22-23. We can have also another method to analyze the sunspots is like the sunspots, they are rotational symmetry. So I don't want to go into details, but they prefer to merge together. Then we have here like an active regions. And so in this case, it is it's also an hypothesis testing, but more a rotational symmetry. And here you can use then, for example, this test that I mentioned here. Okay, there are also other tests. Here in the picture that you can see in your right, so the first one is really like the plotting of the sunspots for the cycle 22-23. And then here, Fernandes de Marques and Gata Portuguese, they analyze really like for every cycle, the uniformity, if there is an uniform distribution of the sunspots. So you can see there are a lot of applications where you can use hypothesis testing. So here in the question that one can ask is maybe the different solar dynamics across cycles. So here it was only tested for 22 and 23. Maybe we need to test also for other a cycle and see in years and really like a deep study of sunspots. Let us come to another thing that is also very important. It is like space debris or space junks. So you know that nowadays we are really like dependent of satellites. The problem is, for example, if you have here solar flares, so an explosion of the sun from this, let me say, emerging of the sunspots, and it goes towards the Earth, then the first thing that are damaged, let me say, that are our satellites. And the damage of our satellites means that we have no more connection with the satellites. And they become then space debris. And this could be dangerous because they can damage, because they are uncontrollable, so they are orbiting really the Earth, and they can damage other satellites, so active satellites. And you can really see here this like simulation that we have more and more satellites. Here we can use direction statistic to predict or to simulate space debris, but because the problem is we don't have data. And one way to do it, it's not like hypothesis testing, but more using direction distribution and models. So in this case, for the spheres. And, Kant proposed this extreme Fisher-Bingham-Kant distribution. So here 5 because it has 5 parameters. And you can see here the simulation results. So we have like this oval density banana shapes. And by ESA, so in the Space Debris Office, approve these models. So it is a good model to really simulate space debris. So this is one way, for example, to simulate or predict this space object, in particular space debris. Another example that is also important is, for example, in satellites. So GNSS is for Global Navigation Satellite Systems. And for example, to compute or to determine the exact orbit of the satellites, you can also use distributional models, in this case in cylinders. So you have then 5, let me say, unbounded Cartesian coordinate, then 1 angular coordinate, so it's a circle. And these 6 coordinates define then the position or the orbit of the satellites. So in this case, for a cylinder, Horwood and all, this Gauss von Mies distribution and also this Marder-Sautin distribution. Another important thing in the, let me say, satellites community is this problem of this real-time carrier phase that can lead to not really precision on the clock that are inside the satellites. And here you can also use distribution models, in this case more on the circle. You have the classical one, the von Mies distribution, the Robert-Cauchy or the Caudieux distribution. Now it's like, okay, what happens if the directional data contains noises? Example is the cosmic rays. So the cosmic rays are the rarest particles in our universe that tell us a lot of information about the origin, also the evolution of our universe. And they are deflected. So that means that the data contains noises, and we can reformulate it mathematical terms by this one. So you have here, this is a noise. It's done in a rotational group of dimension 3. And then X or then data, let's say, without noises. So here that is like the noisy directional data. And Lacour, Negok, and Kim and al., they proposed this noisy direction statistic, and they confront this problem, proposing a goodness of fitness test. And here you have others works that not really use, let me say, noisy direction statistic, but other methods. One particular one is Marinucci and Peccati. It's a book of random fields on spheres. So you can see here in this, for this application, you have a lot more works than other ones. So here, I want not to go in details, but you have also other application. For example, the stars, binary stars or double stars or 2 stars. It's really impressive because they are dancing. There you can also use direction statistic or pool stars, supernovas or an explosion of the stars, then galaxies, so the rotation, the dynamic, and so on. So there you have particle one like the Milky Way halo or the black holes, the Sagittarius A stars. For example, Marder and all the use direction statistic to understand Pluto. So Pluto is not more a planet for our solar system. So the origin of this planet Pluto. And then also extrasolar or exoplanets can also use here direction statistic to understand these problems. So let me give you an overview. So here you can see in the first picture the publication. So there was really a boom in 2000. But you can see it is really like an evolution, and I hope that it will continue in this way and really use directional statistic tools and theory for space science problems. It's also like an overview, the kind of problems and the method used, as well as the manifolds. So you can really see for satellites application, it's more like distribution models. Depends on the problem. Sometimes also in hypothesis testing, like uniformly, if there are uniformly distribution. So you can see here, it's really like giving an overview of different methods used for space science problems. So what is also very important is the data. So here I listed really like where you can find the data. So Grazia Portuguese and Verdebo and also others create this software, not the software, sorry, an R package. And I don't want to list all this data, but here you can find, for example, let me pick one. For the long period comets, you have in this R package SPONIF, then the data is named comets. And also uniformity test, respectively rotational symmetry, you have also R package. This one too, they don't really have directional statistic tools, but I want to listen it because this is like an open, say, project. It's where you can find statistical tools for astronomy problems. Then also some reference. So if you're not familiar with directional statistic, you can find first ones are a good reference to get use of directional statistic and what it is and how to apply it. And then also some reviews from our colleagues, and maybe also some inspiration here at the end. They don't use directional statistic, but more, let me see, standard statistical tools for astronomy application. So what next? So I really encourage you, if you are working on a methods, on a model, to apply it for space science problems. To use the data, it is really available, and it's also free, so you can find it at ESA, also at NASA. Another thing that is very important, and also a good news, that we are getting more and more data. For example, I think you all heard about this new space telescopes, James Webb. We are getting really beautiful picture and also data, but you have also Gaia, Solar Orbiter, and Visual. So Visual is really a new one. Solar Orbiter and Visual, they are studying the sun. There we are getting more sun and also sunspots data. And then I listed also the two open questions that we saw before, so the orbit of the comets and also the sunspots. And I want to close this presentation by a sentence that was in the paper of Figelsson. He really introduced this word astrostatistic. And let me read it. So you say, astrostatistic is the young, fertile field in which interdisciplinary communities can grow, providing essential expertise to further our understanding of the universe we inhabit. I think it is really like an important message. So let us really use more statistical tools or create statistical tools to better understand our universe. So thank you for your attention.